Distinguished guest, welcome to the session on Advanced Materials and Manufacturing, organized under the aegis of the Council of Scientific and Industrial Research. The Government of India has launched several missions focused on advanced materials and their applications to foster innovation, energy security, and industrial growth. Taking advantage of the knowledge and experiences of the champions in this field, we have invited a diverse range of speakers from industry, academia, and government for the session. To begin with, I would like to invite on the stage our session chair, Dr. N. Kalai Selvi, DG CSIR and Secretary DSIR. She has more than 25 years experience in electrochemical power systems, pioneering research on lithium sodium-ion batteries, supercapacitors, and waste-to-wealth technologies. A recipient of prestigious awards, she is the first woman Director General of CSIR. She serves as an inspiration to women in science. Ma'am, you are requested to kindly come to the stage for your opening remarks and set the tone of the session.
Namaskar, Vanakkam, and pleasant morning to each and every one of you. This is a very great opportunity for each and every one of us, and especially to the scientific fraternity, to talk on a very important topic on this particular day, which is nothing but advanced manufacturing and materials. Friends, as all of you know, we are now marching very fastly towards 2047, VII Bharat 2047, wherein this advanced manufacturing and materials is playing a very, very important role. And we as researchers from this particular area should give unconditional support to the country in terms of contribution. Why I will take? Just take the example, 15 years back or 10 years back, we started with the startup number of 150. Today the number is 160K. And therefore India's rank is number 3 in the globe with respect to the number of startups. And the story doesn't end over here. If you just take our growth with respect to certain areas, if you just take the goal of our country with respect to various agreements, by 2030, India's total energy capacity should be managed to 50% by renewable. Today, we have reached 234 gigawatt of renewable energy. 50% of renewables we have already accomplished 5 years ahead of target. How is it made possible, or how it is getting possible? It is just because of the kind of importance, the kind of awareness that is really reaching the nook and corner of the R&D society. I mean to say it is not only the today's researchers, but also the researchers of tomorrow. And if at all we just take the case of the success stories of our country, especially with respect to manufacturing, the country is now having a clearly planned canvas on which we have boldly written that we will be able to come up with success stories in at least 4 or 5 areas. So whether you take in terms of energy security or water security or food security or healthcare security or strategic security, and I would add even data security, I think the country is having the complete platform in its preparedness because we have the young and the energetic, intelligent and smart workforce in the name of startups, it is coming as smartups, so that is also correct, startups, MSMEs and also industries. To celebrate this particular group of industries, startups and MSMEs, we from the research side, the scientific fraternity, from academia, from national research labs, and also from industry-driven R&D, all of us are there as your background supporters. Please take the help of academia, national research labs, and the industry-driven R&D, and please have some kind of a mutual trust in each other. Let us come up with a kind of a working together by means of which we will come up with a number of success stories in the near future. Country has already shown a kind of a success story by way of giving 160 million clean cooking gas to the people. Now the cooking gas, again we can create a new revolution by means of introducing a portion of DME into that. So the country is rich with coal. Can we convert coal? Can we redefine coal? And can we allow coal to transfer its travel from the fossil fuel to renewable energy? If you ask me, the answer is yes. So coal to syngas to methanol to DME to SAF you can take. And therefore it is all only the requirement of planning, working together, and also celebrating together the success. So I'm here to just give you one kind of a confidence on behalf of Government of India, on behalf of Ministry of Science and Technology, on behalf of DSIR and CSIR, just to give only one line of confirmation that we are with you, the same word which was uttered just 2 days back by our Honorable Prime Minister from the same podium to the same gallery. Meaning is we cannot talk in two different languages, and the country's leadership has clearly given the statement. We need not worry about where to go, how to go, what to do, when to do. Everything is very clear. The target is 2047. And again, the goal is Viksit Bharat. And the path is also well set. All of us should work together. So taking this opportunity, I really want to place on record my sincere appreciations to the Department of Science and Technology and to each and every one of you on a close to holiday. This particular auditorium is getting decorated with these many intellectuals means this is the strength of Indian science and Indian technology. I'm really getting motivated by looking at each and every one of you. The time that we are going to invest today here in this auditorium, every minute and every word that is going to be discussed in this particular auditorium will have its impact in the coming times. With these few words, I take this opportunity to thank each and every one of you, and the stage is now open for further proceedings. Thank you so very much. Namaskar.
Thank you, ma'am, for your opening address. We shall begin our thematic session with the keynote address that will be delivered by Professor G.U. Kulkarni, former President, JNCSR Bangalore. Professor Kulkarni is a distinguished scientist whose work has contributed immensely to the field of advanced materials and innovation. He served as the President, JNCSR from 2020 to 2025. He has held honorary positions at institutions including Cardiff, Tokyo, Triesta, Pisa, and Paris Sud, and also served as an adjunct professor at the Purdue University. He has over 340 publications on nanomaterials and devices. He's fellow of all major science academies and a J.C. Bose Fellow. Sir, we invite you to the stage for your keynote address.
Thank you for the introduction. Good morning. It's a pleasure and honor to speak before this august audience in a session chaired by DG CSIR, Dr. Kalai Selvi. I am thankful to DST Secretary, Professor Abhay Karandikar, for the invitation to speak as a keynote speaker, and also for the invitation to chair the thematic area itself. Thanks to all the theme expert committee members for their efforts to put together a program. You will witness now a very stimulating series of talks and panel discussion all through. I'm sure you will enjoy. And I have chosen to speak, I think the control is with me only. No. Yeah, so let's get started. I have just about 15 to 17 minutes or so. I would like to allow a few minutes in the end for question answers. The topic I chose, sort of suiting the theme area, is how we realize functionality of materials, particularly advanced materials, and how we take them to product realization. A much sought after topic for the country, for the globe itself, and I thought I'll be able to give you some insights into this activity. Before I do that, it's also my pleasure to mention that a vision document is being released this evening by the Honorable Minister of State, Science and Technology and Earth Sciences, Dr. Jitendra Singh. And this document was initiated by Department of Science and Technology, by the Nano and Advanced Materials Division. They formed an a group which I had the honor to chair, and working for the last 1.5 years, consulting several experts across the country, brainstorm sessions and whatnot, we could put together a document, somewhere around 250 pages or so, what country could be doing, it's a roadmap, what country could be doing in this important area. And let's witness the release of it in the evening. And I would like to just mention in this meeting that we were pleasantly surprised that there are around 5,000 more research groups in the country, from various institutions, R&D labs, private labs, put together. This is actually slightly underestimated. I would say even more than that. And I can even support the argument because when there was a little call from DST, we had very overwhelming response to it. We had more than around 3,300 proposals being sent. So this is a very realistic figure. It's not very hypothetical. So somewhere few thousand groups certainly are working in this important area, advanced materials and manufacturing. And in the document, we have covered various sectors are listed out there. We have given strategies, the vision, mission, and all that. It is as per the government, the format what is defined. And I'm very, very hopeful that DST, joined by several ministries, would be taking it forward for implementation. And we identified several thematic areas in this vision document. They're all listed out there. I don't have time to really go through. And these are all the verticals. And then there are two horizontals, one related to computation, the other one is advanced techniques. In fact, the figure is the other way around, if you don't mind, okay? So the horizontals are standing vertical, doesn't matter, but this is essentially the structure of the vision document. And once it is released, you will have access to see it, and we'll be happy to receive your feedback and comments. Yeah, having made the document, in our interaction with PSA, Professor Sood, we realized that we have to really strategize, okay? I mean, we can't be doing everything. So we also came up with a section on how to prioritize. It needs more discussion, more consultation before implementation. So let me not take you through the whole discussion. I just want to highlight that we need to strategize given the vastness of the field of advanced materials. One or two tutorial slides. There is often confusion. What are advanced materials? I mean, given that everything is material, so to say matter, what is a material and what is advanced material? Since I am the opening batsman, let me do justice to this. When we realize property of a piece of matter, it becomes material. When we realize the hardness of a stone, we know how to make a tool out of that, right? So then it becomes a material. And when it becomes an advanced material, for sure we will have a control on the composition at the atomic or molecular level. We'll also have control on the size. We know how to realize quantum size effects and control over the shape itself, the morphology, the shape, and importantly, the dimensionality. So graphite is one, graphene is another. We heard a wonderful talk on wonder materials by Sir Andrew Guy. So a simple piece of matter can become an advanced material the moment we learn how to control, derive very exotic, interesting properties, and how to exploit them in technology frontline. Long way actually, if you look at the whole history, we learned the act of survival and how to utilize the matter around us. And since then, we had, industrial revolution, industrial level manufacturing. But I think the time has come now that every little lab invention should be driven towards technology, and that needs a tremendous collaboration. As DGCSR mentioned, that it needs a synergy and collaboration across several groups in the country and also globally. And we now talk about technology readiness levels right at the beginning of conceiving the idea itself. So I think it is very important that it is not after realizing something, publishing a paper and running around with, having a patent granted, we start thinking what to do. Probably not. I think most of the ideas would deserve a bit of thinking at the ground level itself, okay? Can we actually see this particular invention, if it is born, can it see the light of the day? Okay, so can we make it walk through the TRL levels? A bit of thought would certainly will help. When we talk of advanced materials today, I mentioned, ways of, controlling the properties and whatnot. There are many ways of actually deriving advanced materials, be it silicon-related, gallium nitride, graphene, so to say, making composites, polymers, mixing, bio, polymer, plus inorganic. There are many, many ways. That's how the diversity of the advanced material field has come up. So to this crowd, I don't need to overemphasize. My speakers in the session following me would be covering these topics. Having said that, there are very readily identifiable products out there. I don't have to bring examples from the outside world. We all get to see them, which were non-existent, say, a couple of decades ago, and today we use them day in, day out, right? So these are all because there was tremendous research done in the area of advanced materials, and people learned how to take these things forward, translate along the path, and finally realize as products. These pertain to various sectors, whether it is energy, infrastructure, electronics, EV. In India also Government of India has launched different initiatives and missions pertaining to some of these aspects. In fact, when we wrote the vision document, we carefully didn't emphasize much on quantum materials because there is a quantum mission, and also critical minerals. No, we just give mention of that because there is a parallel activity. So is the case with EV, okay? So these are the sectors where advanced materials would make a huge difference. I don't want to stick to too much of general talk. In the remaining minutes, I want to bring out an example from the laboratory itself, from my own group. This is an example which would relate to everyone, how to take a piece of glass and make it smart. Glass, as we use it extensively, in all sorts of applications. We use it because it is very inert, right? It stays for years and decades and centuries. But on the other hand, being so inert, it is not very participative in whatever you want to do. So how to convert glass into a smart glass is one of the activities we initiated a couple of years ago, and I'll just tell you the gist of that. Glass, it remained not much used in the past, but today we use it in infrastructure development. Buildings are covered by glass, and glass at best can get toughened, not beyond that actually. So that's about the nature of glass we are using today, but it is being extensively used. So if you want to make glass smarter, how to go about? We want to make it smart in the first place because we want to use it in various contexts. Whether, there is so much of light outside, but still we have to turn on these floodlights to illuminate me and the audience. So can we have smart glasses and not have covered the roof itself to allow mild light to walk through, and we can save on energy? Possibility. That will also have influence on air conditioning as well, right? Heat management. And there are other aspects like privacy control, whatnot. We build partitions and again put lamination on top, but they remain very passive. We can't control these partition, whatever structures we make. So these are the ideas which stimulated our thought process. There are solutions in the market. You look at photochromic glasses or thermochromic windows. These are solutions actually, but again, there is no user control there. These are passive devices. They just function based on other parameters. Whereas there are active devices like electrochromic windows. A couple of aeroplanes you may have come across which use this technology for passenger windows. And PDLC, polymer dispersed liquid crystal windows, is already a reality, and that's all around. So what I'm speaking on basically, why should we really worry about? I've given some benchmark parameters. There are a dozen more parameters to compare actually. I'll not get into that. Why we are not having PDLC all over the place? Something is prohibitive. It is based on electrical energy, and that electrical energy comes from electrodes which ought to be transparent. The problem is glass is transparent, but not electrically conducting. If you want to make it electrically conducting, you have to coat a layer. The God-given material, indium oxide doped with tin, is the material. It was discovered some 6-7 decades ago, and that's the material we are using even now, and that forms a layer in your smartphone as well. So this is the issue. That is very expensive as silver is. So you don't want to use that and throw it in trash. We throw a lot of electronic trash and that goes waste. Silver is recoverable, whereas indium is not. It is as abundant as silver itself. So these are some thought processes why, you can't be routinely using ITU coating on glass to make it conducting and make these technologies viable. What we did, we realized that we could have some templated process of realizing nanowire networks of metal wires, cheap metal wires, and make the glass conducting, okay? So we used colloidal dispersions, which are available in large quantities, very cheaply, environmentally benign and all that, and bring a thin coating on glass and allow it to just evaporate. The solvent goes away, you will get desiccated crack patterns. You have to optimize the conditions such that all the cracks are interconnected, and now you can use it as a template. The moment you shower a metal chemically or physically, for example, aluminum, and wash away the template, you'll be left with very fine mesh of aluminum wires, not visible to naked eye, but it makes the glass surface conducting. Good enough for many, many applications. We have demonstrated, if you walk into my lab, you will have actually a prototype gallery wherein you can play with the touch screen and realize yourself. We have built solar cells, all that. So basically it can replace ITO, particularly in the graph there, it should be appealing to the industry. When it comes to deriving very low sheet resistances with reasonable transmittance, optical transmittance, ours is the best. We have shown that if you want to come down below 1 ohm per square, you have to be coating very thick ITO. You also lose on the transmittance, but while we do the best. Well, having said so, this also uses electricity. So this is a lab-made prototype. You can see it switching. This is a PDLC window layer which is switching here, but this also uses electricity. Not a good news for all electrically stimulated devices. My passion was to make something. Glass per se doesn't use any electricity for its existence or for functioning. Can you have glass switch transparency at the same time not consume energy? That's truly a challenge. And after pondering over this idea, we came across a possibility. This was just a thought process, so to say, a high school experiment, but eventually turned into a product, nearly a product. Okay, this depends on make use of a glass which is purely transmitting as it should, and roughen the surface. Once you roughen the surface, it scatters light, it becomes translucent. From 90% transmittance, it comes down to around just about 2-3% scattered light, and you will not be able to see anything on the other side. This kind of blasted glass, they are called, or laser engraved glass, whatever, they are used everywhere, okay? So, but we had to work on the scientific method because we didn't want to change the refractive index on the surface. Eventually, the idea is to fill in these cavities on the transparent glass, which was roughened, with a liquid which is refractive index matched. The moment you do that, you will not even know the presence of the liquid there. Okay? So basically create a microfluidic cavity between two glass panes and make this liquid rush through. You will see transparency switching happening there. There are many scientific facts to work with there, particularly in interaction with industry. This is what I want to emphasize to students and young colleagues here, that early on, if you catch on and talk to industry, there are many lessons to be learned. It's not about the basic idea to realize how glass can be made to switch its transparency. It's also important to make it very elegant. When we push in the liquid, it forms all sorts of fronts. It gives dendrimeric structures and all sorts of things. Finally, the consumer wants, consumer doesn't want to see the liquid actually. Consumer only wants to see the switching glass. So how to make it possible? Several considerations we had, and this activity went on for nearly 2 years, and later on we could realize a prototype working like this. You see, it's not bad, right? This is made in the lab, actually. So you can see not only the transparency is switching, you can actually roll the curtain down to a level you like to. So curtain rolling technology is non-existent in any of the smart windows unless you pixelate it. Okay, here there's no pixelation, and extremely importantly, there is no consumption of energy there. I must tell you, the interaction with industry wasn't that smooth because they hold the gun here. I mean, it's not that straightforward, not because they give money for the research part and they also ask you the deliverables. And that's a tough game actually. And I must say, I really enjoyed the journey itself, taking it through different levels of TRL and this was the interaction. So this is Saint Gobain, India, and we collaborated on this particular project with them, and we could make big prototypes working with them. So where is the take-home message here? The take-home message is no energy. If you want to keep the glass in a particular condition, no energy. If you want to operate it manually, no energy required. Only when you want to switch, probably you want to activate some circuit, you may need a couple of watts. That's about it. Otherwise, it's a zero energy device, and it is working very well. The company is moving forward to actually go for customer feedback. I hope things will look up as we move on. So, last slide. As we all should be contributing to our important national missions, Make in India, Atmanirbhar Bharat, I think it's time to actually focus on whatever we do in the laboratory. Right at the genesis, the sprouting level, we should look at how to translate and take it forward. There are many worries, many things. We can have brainstorm session, we can consult experts, do whatever, but I think the focus should be translation. Otherwise, working in the field of advanced materials may not really take us anywhere, except for some good couple of publications and H factor and whatnot, but the country will not move forward. So this is an appeal, particularly to the younger crowd here, to contribute towards technology translation. With this, I would like to thank my co-workers and also all of you for your kind attention. And if time permits, I will take maybe just a few questions. Is there time? There's no timer there. Okay, they're kind enough to allow one or two questions, but I shouldn't be really, cutting into the time slots of other speakers.
So we shall start with the
Later?
speaker. Yeah.
All right.
Hello.
Fine. Thank you.
Sir, one question we can take. Is it okay?
Okay.
So if there is any question, only one we can allow.
I am Dr. Malati from CSIR NML. Sir, I would like to know what is the cost of production of this microfluid which we are producing it.
Very good question. It is almost as costly or as expensive as the glass itself, plain glass. Hardly any cost addition to it.
Oh, good.
Thank you.
Good, sir. Thank you. Sir, and one more thing, what is the mechanism that it stops to move from one...
You just stop pushing in the liquid inside, that's all. You push in the liquid as much as you want,
Okay.
transparency comes, and then you stop wherever you want.
Okay, there is a switch or something?
Why don't you visit my lab?
Okay, sir. Thank you for
Thank
calling
you.
me.
Thank you.
Thank you, Malti. Thank you. Now over to you, Deepti.
All right.
May I?
Thank you, sir.
Thank you.
Thank you, sir, for your inspiring keynote address. We now begin a series of talks by eminent leaders from the domains of startups, entrepreneurs, and science and technology leadership. Our first speaker is Sri Pavan Kumar Chandana, who is the co-founder and CEO of Skyroot Aerospace, India's pioneering private space launch company. He holds a dual degree in mechanical engineering and thermal science from IIT Kharagpur. He began his career at ISRO's Vikram Sarabhai Space Center, where he worked for 6 years, contributing to critical missions. In 2018, he co-founded Skyroot. Under his leadership, Skyroot has scaled to a team of 600 plus space professionals and is advancing the Vikram series of orbital launch vehicles. Sir, we request you to please share your journey of innovation.
Good morning, everybody. It's really wonderful to be here. It's good to see like the entire science and technology community from India coming together for 3 days. It's a great celebration for all of us, and also to see wonderful announcements happening every day. It's great to be here. And as a space person, I'll be talking about 2 very important technologies which we have used a lot, and I'm sure like these are very applicable for every stream of engineering. And these 2 are, one is using advanced composites to reduce weight, and the other is use of 3D printing. Of course, all of you might have heard it, might want to use it, might have already used it, and I'll show how we have harnessed these two powers in building our launch vehicles, our rockets, which we have done so far, and also we can see what can be done in the future as well. So in fact, when something's very, very hard, we say it's like rocket science, and that's the industry we're in. So space is very hard, rockets are very hard, and if you build a rocket of 100 tons, you can launch only 2 tons to orbit, and to improve the efficiency of the rocket, you need to build the rocket very, very, very light. It has to be extra light, despite, being able to withstand the rigorous environment of space, rigorous environment of atmospheric flight. It has to be super light. And I think space materials has to be very smart and a lot of innovation to happen there. And that's where I think one of the key technologies which we pioneered in space launch vehicles is, use of carbon composites. And just to give an idea, like carbon composite is today like, 5 times has more strength than the strongest steel, and it's 5 times lighter. That's just imagine the kind of, power it can have in, building lighter parts, especially space vehicles. And today it's, because even if you build anything with carbon fiber, you have to have some metallic joints, etc., which increases the mass. But carbon composite per se is like extremely low weight, and you can build, parts, or you can build entire systems as half of it, and even 1/3 of the mass of the entire system as before. And it saves a lot of fuel, and it is makes it very efficient. And in fact, when we fly an aircraft, we can see like most aircrafts today are using carbon composites. And if you see, a few decades ago, hardly there was any carbon composite components on air flights. And now we can see like more than 50% of aircrafts like 787, Airbus A350, the large aircrafts are mostly built with carbon composites. It looks like how technology can, empower everyday flight as well. So this is our rocket, which is going to launch in the coming months. This is a privately built launch vehicle, which is 7-storied building tall, and it's completely entire airframe, entire structure of it is completely built with carbon fiber. And this is the first time in the country, in the space sector, where an entire rocket of orbital grade has been, fully built with, carbon fiber. And we have seen, we have witnessed the power of it as we built it. It took us so many years to, master it, and we know how difficult it is to make it happen. And finally, it builds a very, very efficient rocket. This is at our factory. In fact, at our factory, carbon fiber comes in and rockets roll out, and that's the kind of, and we use a lot of automated machines to cut the fiber, to lay the fiber, and also to build the entire rocket layer by layer, and there's very little wastage in adding layer by layer composite and building a rocket. And this is soon going to launch, and request all of your blessings for this one. And this will probably build, put us among very few companies, maybe 5-6 companies in the world with the capability to launch satellites in orbit. And the other wonder technology, magical technology is, 3D printing. And in fact, rocket engines are one of the most complex, engineering marvels. And typically when you build a rocket engine, you have hundreds of parts. And typically, and all these come together, you need to weld them, you need to brace them, and all these, every joint is a point of failure. And then now new technology comes where, you can actually build the entire 3D printing, entire engine using 3D printing in just few days. And this is one of the engine. This is a VII series of engine. We have built India's first privately developed cryogenic engine, and this is fully 3D printed in single component. So every rocket engine, just imagine it needs an injector which will spray the propellants and mix them very well. And then you need, inside there's 3000 degrees centigrade. You need to cool the chamber. To cool the chamber, you need like various kind of, channels to cool it, where the fuel will come and cool it. So very intricate geometries, very intricate design, all coming together. Everything is printed, magically powder comes in, and the laser stitches it to build a 3D part in just few days. It's really marvel of technology, and we are able to integrate it. In fact, we built at least 7 different types of engines, as small as few newtons of thrust to as high as several tons of thrust, all in 3D printing. And in fact, like this has really helped us push our boundaries of innovation, reduce the failure points, increase the reliability, and also reduce the production times. Typically, even just the tooling for building a traditional engine could take as high as few months. And then in 3D printing, there is no tooling required, and it could, if you develop and manufacture new engine, could take as a cryogenic engine especially could take as high as even 2 years. And now, like 2 years with 3D printing magically becomes just 2 days. So that's the wonder of technology. And hundreds of parts becomes just one part. I think so. That's also something which is really beautiful to see as it comes together. And then the rockets build and fired, and we have done so much firings, and we know how important this technology is. And once upon a time, when we started it, there was a lot of skepticism. Is the technology matured enough to be able to build rocket engines? But now, like when we go to our engineers, everybody says, no, next engine we have to build it. Everything with 3D printing. I think the paradigm has completely shifted, and this is, I think, a new technology which is powering a new generation of rockets. And then from concept, I mean, this all started as a concept, and then on November 18th, 2022, we have created history by launching India's first privately developed rocket to space. And this rocket is fully built with carbon fiber. So the entire structure is built with carbon fiber. First time again in the space sector in India, and has several 3D printed components, successfully took flight, put us among very few companies in the world who has successfully built and launched a rocket to space. And this rocket, which was called Vikram S, which was 2-storied building tall, it was a test rocket. It was designed, developed to flight, everything within just 2 years. And in fact, our Honorable Prime Minister called it a historic moment for India, where private companies are able to design, build, launch a rocket to space. I think it's a historic moment for the entire space industry and for India as well, and also shows the potential of how a startup can come together, put talent together, do hard things, and achieve great milestones across the world. And our journey just started with 2 people, me and Bharat. We started the company 7 years ago, and now we are almost about to reach 1,000 people team, and then we have and we never imagined that you can even raise capital for a very deep technology. In fact, like our revenues are going to start only next year, and we have so far been able to investors have been kind enough, and they have been like very bullish enough in the space industry and in us that we were able to raise the largest amount of funding by any space tech company, almost like close to $100 million of capital we're able to put in through to design, develop, build rockets in the country, and then employ hundreds of people, now getting into thousands of people right now, putting in fact a lot of materials engineers working with us, putting this together. And then this is a rocket which we are going to launch in few months, 7-storied building tall, like I mentioned, and like our Honorable Prime Minister has put a goal for the space industry that in 5 years we need to do 1 launch every week, and fueled by the private sector as well significantly. And I think Vikram 1 is going to take flight, become the first ever rocket in India by the private sector to be able to put satellites into orbit. And then it's also going to increase the number of flights per year as we go further as a country, where we have capability to do more number of launches from our own soil. And in fact, more than 90% of the customers for this rocket are global. So we're building a very deep technology product from India for the globe, and also put ourselves in among maybe 5-6 companies in the world having this capability. I think again shows, I think, very proud to be doing it from India. And this is just the beginning. And in fact, the future, in these technologies is we'll have a lot of 3D printing. We have a lot of, carbon composite being built. And I'm sure all of us use ChatGPT. In future, I think design also will be driven by AI, where we try, build this rocket structure in these constraints in this particular time and give the manufacturing instructions. And I'm sure, we're going to get a much more optimum designs going forward. It probably is a few years away, and that will enable us to build things things faster, better, AI-driven material developments, AI-driven manufacturing is going to come into the future, and then self-healing structures, and also, carbon composites are already very stronger, and there are a lot of technology where we can even make them even further stronger. We can mechanically interlock the fiber and the composite and the matrix together using nanofibers, using nanomaterials, and you can also have self-healing structures where even if there is damage, you can even, they can heal on their own. So these are all the future technologies which we're looking into to even push boundaries further to make them even stronger, better for the next generation of launch vehicles. And also, we all think about space. We all think geocentrically. We think Earth is everything because gravity pulls us together, and rockets are the magical creatures which defy gravity and take us beyond Earth. And we believe strongly that the next frontier is space, and we all are going to become a multi-spacefaring civilization, multi-planet civilization, and there'll be manufacturing happening in space. There'll be people living in space, and there'll be a lot of excitement happening in space. I'm sure like all of you will go to space in their lifetimes. Your grandchildren definitely will go to space in their lifetimes, and this is the future which we're going to create. And the future in space as well is again additive manufacturing and carbon composites, because we need lighter structures, we need 3D printer. In fact, there are a lot of concepts of how we can build homes in moon using 3D printing, how we can make materials in space using 3D printing, because typically you can even build organs in space using 3D printing because there's no gravity, and you can produce better, better structures with more stable structures. And just space manufactured products in few years is going to become $30 billion business alone. So I think and it's all be fueled with additive manufacturing again. So I think it's beyond from Earth to space, and even beyond. These are the technologies which are going to power the future. And I think we need to build smarter, fly higher, and we need more startups coming up. In fact, thanks to the Honorable Prime Minister, when we started, there was not even a policy for the space sector. 3 years ago, it has come, and we started launching rockets to space already. And we're going to increase the frequency more and more, getting into the few companies in the globe doing it right from India, right from Indian soil. And right now, as the government opened up the sector, more than 300 startups have come, employing more than 4,000 people just in the last few years. I think this is again the power of policy, power of startups all coming together in a very short period of time. The future of India is bright. And in fact, 65% of India is below 35 years old, and sky is no limit for the young crowd in India. Thank you.
Thank you, sir, for your engaging and inspiring presentation. Our next speaker is Ms. Rajashri Bojraj Teli, who serves as Joint Managing Director of HYT Innovative Projects Private Limited and Managing Director of HYT Engineering Company Private Limited. She has immensely transformed the HYT group through leadership. Her companies operate India's largest flow-forming facility for defense and aerospace components. Madam is a noted woman entrepreneur in advanced manufacturing.
Respected dignitaries from academia, research, fellow industry members, and all those who contribute tirelessly to the nation's progress, I, Rajashri Bojraj Teli, extend my warmest greetings to all of you. I am here today presenting HYT's Defense Division to speak on the theme, Blueprint to Breakthrough, when precision becomes a national duty. I will be sharing our journey from pioneering the flow-forming process as India's first private sector company to build what is now the country's largest and the most advanced flow-forming facility. Now, every breakthrough begins with a moment. To elaborate the moment, let's travel back to the year 2000. It was the dawn of a new millennium and the beginning of a new industrial era. India was emerging from a decade of liberalization and reform, experiencing political and economic stability through GDP growth, industrial revival, low inflation, and strengthening reserves. Even though foreign relations and diplomacy advanced, cross-border tensions persisted, and this called for greater self-reliance. Despite these challenges, the year 2000 also marked the beginning of something extraordinary. The government began allowing private sector participation and foreign investment in defense manufacturing. That era marked more than policy reforms. it marked a mindset shift. For decades, we looked outward for technology, design, and defense solution. But the new era asked us a question: can India design, engineer, and build for itself and for the world? This was the environment in which HYT Innovative Projects Private Limited emerged, an initiative aimed at translating manufacturing excellence into indigenous defense capabilities. Our very first assignment was quite unexpectedly the reconditioning and commissioning of a flow-forming machine, a process and technology virtually unknown in India at that time. Yes, we had the background in machine tools, but flow forming belonged to a different realm of advanced metal forming technologies combining material precision, material science, and controlled engineering. Flow forming process was considered an untold process practiced by a handful of European firms, largely classified to its defense applications. There was no reference of this process in any of the engineering books or research papers. To those unfamiliar, flow forming is a precision cold form metal forming process in which a thick-walled cylindrical or conical preform is plastically deformed and elongated over a rotating mandrel. Specialized tooling, like hardened steel mandrel and 3 to 4 forming rollers positioned symmetrically, make the material flow into the desired precise shape. This process is fully CNC integrated with closed-loop servo drives. Parameters like mandrel speed, axial feed rate, radial forming force, velocity play an important role in reducing the wall thickness up to 90%, that too at ambient temperatures of 20 to 40 degrees Celsius. Unlike machining, which removes material, flow forming redistributes material under cold working conditions. The result is a thin-walled component with exceptional dimensional accuracy, surface finish, and enhanced mechanical properties. The grain elongation along the forming axis enhances yield strength by 25 to 40% and improves fatigue life up to 2.5 times as compared to machine parts. The typical tolerances of flow form components are roundness of within 100 micron, wall thickness uniformity of 30 micron, and surface roughness of 0.4 to 0.8 micron RA. Concentricity and straightness within 0.1 mm for a length of 1 meter. Due to this, it is widely adopted in aerospace, defense, and energy sectors globally for producing components like missile casings, rocket motor tubes, high-pressure cylinders, where strength to weight ratio, uniformity, and reliability are mission critical. When HYT encountered this technology, India had no indigenous experience or literature on it. There were no design manuals, no suppliers, no tooling reference. We began from a clean slate. Now, our original task, if you remember, was to recondition a flow-forming machine, and we executed it successfully by getting the machine back to its original parameters. Due to the absence of simulation software at that time, the only way to validate the process was through multiple iterations of operating parameters. We learned faster than we failed, and eventually, in the year 2002, HYT made flow forming a success and a national achievement. Encouraged by this, we extended our expertise into flow-formed components, producing flow-formed defense components and establishing India's first private indigenously developed flow-forming facility in the year 2003. For this project was not just a new venture for us. It was a multidisciplinary engineering pursuit. We had to understand mechanics of plastic deformation, material flow behavior, mandrel metallurgy, and control system integration, all without former prior exposure. We didn't just replicate, we developed the total manufacturing and process engineering. The products developed by HYT Innovative are a significant achievement in itself. One of our first projects was to manufacture the thin-walled tubes for BRC. I'm proud to state that back in 2003, HYT Innovative was the first company to successfully develop this product. Our next development was for the iconic Pinaka rocket systems. We developed motor tubes for all 3 variants, Mark 1, Enhanced, and Guided. Here we control the ovality of ID within 0.2 mm while forming on electroslag refined grade material. Back in 2004, we were the first, and I'll repeat again, back in 2004, we were the first Indian company to develop the Pinaka rocket motor tube. What began as a single project quickly evolved into a technology platform, one that could serve multiple critical programs. We began contributing to components that demanded not just accuracy, but absolute reliability. Next for HYT was development of thin-walled tubes for long-range surface-to-air missiles. The challenge was to control the concentricity along with the circular thickness variation at any cross-section within 50 microns. The straightness to be achieved was 0.25 mm per meter without any machining operations. In spite of various challenges, in 2006, HYT Innovative Projects was the first Indian company to successfully develop this product. HYT was pioneer in developing the rocket launcher barrel tubes used for naval rocket launchers. The challenge here was to achieve mechanical properties of tensile stress and proof stress. In 2008, we also attempted the most challenging project of manufacturing PJ-10 booster shells for the BrahMos missile program. Here we had to achieve conical shapes through forward forming and achieve concentricity. I'm proud to state that HYT was the first organization in India to develop the booster shells for BrahMos. Transitioning from high-grade steel to use of aluminum alloy, from conical shapes to parabolic shapes, we developed the envelopes for SPICE 2000 guided bombs, which were used in Rafale. The challenge here was to understand the process response to a new aluminum alloy and avoid distortion. In addition to flow forming, these components had to go through precise drilling operation. Here too, we were the first to not only to develop, but also to export this product. The next and our latest development is the rocket for naval application. Our scope here is to manufacture all the components and even execute the sub-assembly and assembly of the rocket. It includes some special process like protective plating and coating. With this project, we have demonstrated our capability not only for precision manufacturing, but also for critical assembly of rockets. Apart from the flow forming process, HYT Innovative Project has ventured into thermal insulation lining like EPDM and silica. So basically, this thermal insulation is applied on the inner side of the flow form tubes in order to protect it from the heat generation during burning of solid propellant of rocket motor. The question all of you may have is how a company from Pune developed this breakthrough technology and opened the doors for self-reliance in defense manufacturing. Many think of us at HYT as researchers or scientists. To be honest, we are none. We are just a bunch of stubborn engineers who enjoy taking up impossible projects and turn them into a success, come what may. Through various applications, we have demonstrated that advanced manufacturing technologies can both be indigenous and world-class. As we look ahead, the journey of flow forming is far from over. In fact, it's entering its most exciting phase yet. As we speak, the process is being integrated with Industry 4.0 sensors, AI-driven monitoring predictive analysis. Future development in flow forming includes titanium alloys and other superalloys for aerospace application. R&D is ongoing in flow forming of composite metal hybrid shells, crucial for next-gen rocket motors and hydrogen storage tanks. At HYT, our vision is to stand at the forefront of the next evolution and become the nation's #1 defense company. We are working towards developing next-generation flow-forming systems with higher capacities and multi-axis control. We are set to take on global projects and also full platforms, that is manufacturing and assembly of entire rocket systems. Our journey taught us that precision is not just a technical virtue, it's a cultural one. It's about how we think, how we work, and how we take responsibility for what we create. When every researcher, every engineer, and every manufacturer begins to see their work as a national responsibility, that's when blueprint turns into breakthroughs. That's when technology becomes transformation. and progress becomes pride. That's the India we are building, reducing external dependence, creating knowledge, and inspiring the next generation of scientists, innovators, and entrepreneurs. On a personal note, as a proud young entrepreneur of this great nation, I pledge to devote my life's efforts to making India truly Atmanirbhar and to seeing the dream of Vikasit Bharat fulfilled much sooner than 2047. With this, I humbly conclude my talk. I extend my sincere gratitude to the esteemed panel members and the organizers for granting me this opportunity to share HYT's journey on such a distinguished platform. And to the wonderful audience, thank you for your patient engagement and curiosity.
Thank you, ma'am. That was an excellent presentation and insights on flow forming process. Now we move on to our next speaker, Professor T. Pradeep from IIT Madras, an acclaimed leader in materials innovation, an author of 600 scientific papers in journals, inventor of over 100 patents, co-founder of 7 startups, and founder of the International Center for Clean Water. He has also received many prestigious awards, including Padma Shri. Sir, we request you to please share your thoughts regarding advancements in materials.
Wow, what a pleasure to see all these giant leaps the country is making. Let's applaud them. In this about 10 minutes or so, I'm going to tell you about my dreams about matter. Well, I called it as matter dreams at scale for the country. If you start thinking about that dream of matter, of course, I'm a professor, so I'm looking at future. So that matter dreams is creating future. Of course, the matter around us has created our present country and the world. When I look at that world, what is new that one should look at in matter? That matter has to be created sustainably, at scale. When you start thinking about plastics at scale, metal at scale, materials at scale, concrete at scale, we are talking about new kinds of science. And that has to be built, again I said, sustainably. I feel that sustainability can be brought by chemo, electro, mechano unification. And I'm going to tell you give you brief glimpses into that. We created matter with fire. And that matter, that fire gave us thermodynamics, kinetics, and engineering. And that gave us mobility, and that gave us modern chemistry and transformation that we just now saw in the previous lecture. This is Anton Lavoisier, the father of modern chemistry. Now, we have built the world with that chemistry. So this is Tata Steel. But then it has also created numerous problems, as we know. And that world is now changing. How is it changing? Well, it is changing because matter is becoming atomically precise. So today, with a few atom molecules, today you can build a car engine. It's possible to create a body with atomic precision, materials of atomic precision made in bottles. Bottles meaning chemical reaction vessels. This is a 17-atom silver molecule we make in the laboratory. But you can assemble it in many ways to create your jewelry, for example. Now, this is the science of the past 10 years I'm talking about. At 2047, what will that science be? Today, such materials are called quantum materials. We make them in the laboratory. We measure their mass spectra. We understand their great details. We do great many science with this. Now, today they look like this, but they can be put through microscopes and you see an ocean of these particles, Avogadro number of these particles, extremely uniform. This is like grams and kilograms of these materials can be made today. And that story is growing. Today we make crystals of this. And this, 2 years ago, it won a Nobel Prize. Today, you can engineer matter of very many kinds. But that matter, as you can see, can build, that are called clusters. They can build cluster dreams. This is built with a few elements of the periodic table today, but periodic table is full of those elements. Imagine each one of those elements give you numerous properties, numerous kinds of wonder materials. If periodic table can be made into these cluster forms, what are the wonders awaiting? Remember, the entire biology is built with just 5 elements. We have all this variety of this planet because of these 5 elements. But if you are in a position to modify, engineer with 80 elements that we can harness, imagine what you can build. Today we are making these atomically precise small pieces of metals. We are making powders which are luminescent like this. And we are making those flexible electronics. We are even in the process of making new chips or memory devices. But imagine if you are in a position to put different metals into a small particle. This particular particle there can give you different kinds of catalysis. One atom or one side of this particle will give you new polymerization. Some other part will convert CO2 to methanol, for example. Numerous kind of things. But today, organic chemistry has advanced tremendously that you can have single atom synthesis to make a carbon nanotube like this. Think about this. This is organic chemistry making nanostructures like this. Is it possible to have such chemistry for the entire elements of the periodic table? What kind of world can you build? They are addressing sustainability challenges. For example, Akira Fujishima says that TiO2 of some years ago made the world white because of the pigments. But today they are becoming molecular. And the whole world can be with these kinds of paints. Today at IIT Madras, we create advanced materials which solve problems of the planet like clean water. We provide this to millions of people today. And they look like these plants. But I ask this question, how can new sustainability be built? I'll show you one example that can water create materials? So here is a paper that we published last year, which simply said that take sand, and the sand can break into nanoparticles just by droplets of water. Take a droplet of water and put sand inside it, charge the water droplet, what you create are nanoparticles, as you can see. So you see, nature makes these nanoparticles too. But nature makes sand from rocks in millions of years. But I just showed you that rocks can be made, minerals can be broken into nanoparticles in just 30 milliseconds. And that would mean, let us say a meter becoming a millimeter is like a scale of 1,000. A micron-sized particle becoming a nanoparticle is also a scale of 1,000. This can be achieved in millisecond time scale. So I said, take this rock and put it in water droplet, and we asked this question, what rock to be put? We took the mother of all rocks, that is sand. And that is the sand that we take, and that is powdered into micron-sized particles, and put this in a spray device, and what you get are nanoparticles. This is not just sand alone, this is ruby which makes nanoparticles, or synthetic alumina which make nanoparticles. What happens? What is happening is that in a droplet, if you put a small particle there and charge it, the charges repel each other and the droplet breaks, and when the droplet is breaking, there are large pressure fluctuations of the order of 200 megapascals. Assisted by a number of charges there, with reactive species like protons inside this specific crystallographic planes of this particular mineral breaks. Now you can create materials of this kind. So what exactly has happened in this droplet? In droplet, we have chemical factors called chemo, which creates protons, which creates hydroxyl species, which creates hydrogen peroxide, which creates H2O plus. We have pressure fluctuations, as I just told you. We create electric fields as large as several 10 to the power 8 megavolts per centimeter. All of these unite on this micro scale or micrometer scale and create new kinds of chemistry. And people have measured this. This is in this year's some Nature paper saying 50 to 90 megavolts per centimeter. And what kind of new science is possible? Well, when matter is breaking, I just told you one mineral. I work in the area of arsenic removal from water. There are 10,000 minerals of arsenic. How many other minerals are there? There are millions of minerals. Can you break all of them? Yes, we can break all of them. Is water powerful enough? Yes, water is powerful enough to create new matter. So in the laboratory today, we have expanded this. It's not just TEM. We can make this in grams. We can make this in kilograms. We are currently, an Indian industry is supporting us to take this to tons. So now, what kind of world are we looking at? The materials that are produced are creating new kinds of surfaces. On those surfaces, catalysis becomes possible, and that catalysis is going to be sustainable. These molecules that you create could be proteins, could be amino acids. New kinds of biology could be created. This biology could be existing in nature. For example, in raindrops, as matter is being formed there. And maybe this is how biology has created originally, with such new surfaces being born in droplets. So we have a dream. We have a dream to let us say, take sand and make active nanomaterials, which are ingredients, important ingredients of soil. The water is coming from cities, the wastewater, and that would make our deserts bloom. Make soil using wastewater to make deserts bloom. But this is not just soil, this is functional nanomaterials of very many kinds. And if I have time, I will tell you more about it. I will show you this if you are willing to come to our laboratory. But no solvents, ambient conditions, sustainable. Can India initiate a sustainability revolution by unifying chemo, mechano, electro forces? Thank you very much for enabling me to do this kind of science. This was done by our students. Thank you very much.
Thank you, sir, for giving us insight on creation of dream materials with unification of chemo-electromechanical processes. Now we invite the session chair to felicitate the speakers for the insightful presentations. Shri Pawan Kumar Chandana, kindly come on the stage. Felicitation. Professor G.U. Kulkarni, our keynote speaker for the day. Ms. Rajashri Bhojraj Teli, Professor T. Pradeep. Session chair is requested to please felicitate our keynote speaker, Professor G.U. Kulkarni. Shri Pawan Kumar Chandana. Ms. Rajshri. Professor T. Pradeep. Group photo. Now I request for a group photograph, please. We now move to the highlight of this session, a panel discussion on advanced materials and manufacturing, moderated by Professor B.S. Murthy, Director, IIT Hyderabad. Professor B.S. Murthy is a globally known metallurgical engineer with degrees from VII Nagpur and IC Bangalore. He previously held distinguished positions at IIT Kharagpur and IIT Madras, where he established India's first national facility for atom probe tomography. His pioneering research has resulted in 400+ journal papers, 4 books, 20 patents, and prestigious awards including Shanti Swarup Bhatnagar Prize. Under his leadership, IIT Hyderabad is advancing through research excellence, innovation, and strategic global collaborations. Sir, kindly come to the stage. Now, I would like to invite our distinguished panelists to the stage. Dr. Ramalingam Balamurali Krishnan. Sir is an outstanding scientist and director, DMRL Hyderabad. He brings over 25 years of R&D experience in the physical metallurgy of steel and nickel-based superalloys, with expertise in microstructural characterization and advanced materials development. His contributions to defense metallurgy have been acknowledged through prestigious awards including DRDO Agni Award, DRDO Silicon Medal, and the Ministry of Steel's Metallurgist of the Year Award. Welcome, sir. Mr. Subodh Pandey. Mr. Subodh Pandey serves as the Vice President, Technology, R&D, New Materials, Business, and Graphene at Tata Steel, bringing over 3 decades of diverse experience across operations, sales, engineering, and strategic transformation. He holds engineering and management degrees from IIT Kanpur, XLRI Jamshedpur, and completed advanced management programs at INSEAD, France. Welcome, sir. Professor Mandar Madhukar Deshmukh is a professor in the Department of Condensed Matter, Physics, and Materials Science at TFR Mumbai. His research encompasses quantum transport, nanomechanics, topological materials, 2D materials, including graphene, making significant contributions to quantum phenomena understanding. His excellence has been acknowledged through several awards, including IBM Faculty Award and Swarna Jayanti Fellowship. Welcome, sir. Dr. D. Shailaja is a distinguished scientist and head of the Business Development Group at CSI Headquarters, New Delhi, where she leads initiatives to foster industry collaborations and technology commercialization across 37 CSI laboratories. She brings over 3 decades of experience in material science that have been acknowledged through technology awards and the prestigious CSI DAD Fellowship. Now I hand over the stage for panel discussion to Professor Murthy.
Good afternoon, friends. Thank you very much for this opportunity for all of us sitting here to ponder over a very, very important topic on where are we in terms of advanced materials and manufacturing, and what should we do in the near future to be able to reach a stage where we can call our country as Viksit Bharat. As you all know, when people talk of a developed country, India is right now known to a large extent as a service country. I don't think any country has ever become a developed country just by being a service country. So it should be a country of technologies, it should be a country of products. And how do we achieve that? To be able to see that our products are not only sold in our country, that if I go to any country and go to a shop and buy a product, and I should be able to see a product where it is written made in India, that its quality is well respected outside the country, that they are able to use it and be happy with it. So this whole panel discussion today is going to discuss about where are we and what should we do in this particular area to ensure that India not only becomes self-sufficient. I always try to differentiate between Atmanirbharta and Viksit Bharat. Atmanirbharta is more about developing technologies where you reduce your imports. But Viksit Bharat is beyond that, where you develop technologies not only for yourself, be able to be sent to everywhere outside this country. And so we need to graduate from first achieve Atmanirbharta and then graduate further to achieve Viksit Bharat. And I have excellent speakers with me, excellent panelists with me, all of them starting from a basic science gentleman sitting next to me on the left, and a madam who wants to market things, and CSIR, she has been leading the whole team of developing technologies. And I have two people, one who started his life as a microscopist but is well known for making steel for Navy. So DMR steel, which is very famous steel, which the Navy, Indian Navy is using, is all developed at DMRL. And a man who has been there for 33 years in steel industry, where a steel industry which always says, we also make steel. So to ensure that they do many more things, in fact, he also heads a group on graphene, for example. So just to tell you that Tata Steel also works on certain kind of advanced materials of that nature. So I have 4 luminaries around me, 4 stars, and we would like to take this through, and so that we have enough time for the audience to ask a few questions. So let me start now. A few questions. We have noted down a few so that we don't waste a lot of time. So I'll start with Bala sitting next to me. More importantly, while advanced materials are becoming important, okay, do you really think they are such an important area that everybody should focus on that and ensure that India moves in a direction more focused on advanced materials? What do you feel about it?
Thank you, Professor Muthi, and thank you to the organizers for giving us this opportunity to be here and sharing our thoughts with you. I think the stage has been very well set by the speakers before us, starting from Professor Kulkarni and ending with Professor Pradeep. The definition of matter becoming material. So I think the question of should we even look at advanced materials is in some sense a very redundant question, but nevertheless, for the purpose of scientific discussion and inquiry, we need to address it. And of course, as we all know, the three-dimensional, Professor Andre Game started by talking about 3 dimensions and materials. So we live in a material world, and without materials, we cannot imagine civilizations. In fact, civilizations have been named after materials: Stone Age, Iron Age, Bronze Age, and so on. Right now, we are probably thinking of information age, the only age where material is not there. But the information age is driven by semiconductors and semiconductor missions, and we do have a separate session on that in the afternoon. But more importantly, the advanced materials are the ones that let us engineer the world around us, and to create the advanced materials, we engineer the materials themselves. So we have engineering materials and engineered materials, and therefore they are very, very important. And materials again are a horizontal, which is a cross-cutting across all domains. Materials are needed, whether it is agriculture, whether it is defense, whether it is space, atomic energy, everywhere, in all sectors, in all domains, power, energy, whatever you can think of. But materials in the systems hierarchy is very important to understand if you want to push it forward. So just again for that, if we start the lower level of ores and minerals, then we have raw materials, then we have metals, alloys, ceramics, polymers, composites, the whole list that Professor Kulkarni talked about. But then this has been translated into components. I think we ended up, at least 2 of the talks earlier talked about products, the translational research. So we'll have to move them, the components, into assemblies, then assemblies into subsystems, systems, and then platforms. So definitely there needs to be a focus on this.
Thank you very much. So in this direction, when you are talking about materials, predictions also become very important. I remember when I was a BTech student, I was told in the second year BTech metallurgy, you can sell your calculator to someone because you don't need to calculate anything anymore. So from that day, we come to a stage where in IIT Hyderabad, we have a Department of Materials Engineering and Materials and Metallurgy, where we have an MTech program called ICME, Integrated Computational Materials Engineering, where people are trying to use AI to design new materials. Okay, for example, Tata Steel has a big group in the TCS which is focusing a lot on AI for new materials. Can we come up with a new steel? I am sure once upon a time, Tata Steel used to take a long time to come up with a steel composition. Okay, maybe 5 years or so, doing a lot of experimentation. Now they are talking about doing it in a few months. So I would like to ask you, what is the role of AI and ML in the new materials and manufacturing in near future?
Good afternoon, everyone, and thank you, Professor. So we have around 300 PhD students or MTech students who do research in Tata Steel. Even now that I see, while you said 5 years, we are still struggling with 1 year because while we do molecular modeling and DFT techniques for designing organic polymers, for binders, in pelletizing or even polymer coating on steel, but this whole process takes not less than 1 year before we come to a conclusion on the 3 or 4 options that we need to do more research on or do the lab experiments. But I think with the AI coming in and quantum computing especially and the AI models that are coming in, including agentic AI or Gen AI, I'm sure there would be agents now, and I did come across one such application of Microsoft having Azure as a platform. It's an open architect platform where you have agents who do the hypothesis testing, the experimental planning, the simulation, the result analysis, and possibly narrow down the options from millions to maybe 10 or 5, which is now ready for lab experiments. Obviously, the legal approvals and the QA process and the testing process will take time, but this process has really got shortened, and I think it's going to become exponentially shorter as we go forward. So one of the challenges we have, let me give you an industry perspective to it. Obviously, we can't do without blast furnaces, and India, with the growing demand of steel, I think blast furnaces are going to be there for some time. Although there is criticism around the sustainability and the hard-to-abate sector and the coke that is being used there. But coke has 3 fundamental roles in the blast furnace, and one of them is a structural support that it provides, right, to the whole burden as it comes down. So can we use AI, and this is one of the challenges for all of you because I've been pushing this with a lot of researchers, can we design a material which substitutes coke for its structural purpose? Let's say therefore the 1/3 of the coke is not required and it comes out of the slag and then again recycled. It can withstand the temperature of 2000 plus. So is there a possibility of AI doing that? And I'm sure it's not very far off when it's going to happen, right? But why I'm focusing on this point is because India, with its IT prowess and the kind of manpower we have, I think this is an important competitive edge that India can grow, and it will help India to reach the cutting edge of technology. So it's that area, I think, is something we cannot ignore.
Thank you very much. Thank you very much. Now I move on to Mandar. Mandar has been working on 2D materials, real advanced materials. So in India now there is a lot of focus. You remember just about 3 years back, on May 1st, our Honorable Prime Minister in Bangalore announced India semiconductor mission. Okay. From there we talk about, advanced materials for optoelectronics, magnetic materials, variety of them, rare earths we talk about. But in all these, okay, having a right raw materials and materials of very high purity become very important. And India has been depending a lot on outsiders for this. So what should be the direction that India should take in these advanced materials area, particularly in the area of purity of materials, the raw materials that are needed? Can you throw some light on that?
Yeah, thanks. Thanks for the question. So I do work in areas of 2D materials, looking at new kind of superconductors, new kind of conductors, each of them about an atom thick. And over the last several years, there has been a kind of breakthrough in thinking about materials. For example, if you take something which is only 1 atom thick, but you kind of rotate 1 atom thick layer relative to another, you can go from something which only conducts like a regular material to a superconductor. This is a paradigmic shift in understanding of materials. And for that, naturally, it's important to one, do blue sky research, the kind of research that we do in my lab and also broadly at the institution, TIFR, where I am. But for that we require, because these materials have to be very, very pure. One of an example to semiconductors is one of the reasons semiconductor industry works really well is the materials that they work with are some of the purest materials that are made on Earth. Their purity is staggering. So for research and for realizing the kind of functionality that we want from these materials, we want extremely pure materials. And one of the challenges as a researcher, as a material scientist that I face is that we source all of our high purity materials from largely from outside India. And this, if we have to move up in the hierarchy of growing complex materials and developing technologies, we have to be able to get high purity materials, high purity chemicals, high purity gases. For example, this semiconductor industry also needs this. So we need to find some mechanism to subsidize entrepreneurs. When I say subsidize, not just monetarily, but other mechanisms to encourage them to go into this area, because this is a very important sort of basic foundation for us to do cutting edge materials development and research. So there's a definite need for young entrepreneurs, and I would say for scientists to work closely with entrepreneurs, and the government to encourage mechanisms to, for these young entrepreneurs to supply these materials in high purity.
Thank you, thank you. That brings us to the next main important topic. How do we support innovation and entrepreneurship? Just to tell you, at IIT Hyderabad in the last 5 years, the kind of support that we have given has led to about 330 startups with about 1,500 crores of revenue, just coming from one institute, friends. And that brings me to Shailaja Garu, a very important role that she has been playing in CSIR, which is something similar to the Fraunhofer institutions that we all know outside the country, and where something that people like Mandar do in their lab, or Pradeep does in his lab, taken to a much higher scale. So how do we build these scales? Okay, what do you think the roles of labs like CSIR can play in building the scale from a lab scale of milligrams to, let's say, millions, that tons of that I think Subodh kind of people do? What should we do in this direction?
Thank you very much, Professor Murthy. And thanks for that analogy of Fraunhofer Institute with CSIR institution in India. For this seamless translation of technologies from lab to, to the last mile of marketing, we need to change the model in which we are working with a linear R&D model, I would say. Rather, move on to the concurrent development, having translational hubs, in place, such that from TRL4, we can easily switch over through the piloting to the commercial level of passing through the TRL 6, 7 to 8, 9 very easily. So in order to do that, we need to have a system. When I say concurrent development, it means that scientists, engineers, manufacturing, and market validation should work parallelly together rather than working sequentially, which is very, very important. And in order to do that in a concurrent way, we need to follow certain principles. We need to adopt certain models. The first one and foremost is where I would say that we have to bridge this gap of trying to bring pilot plant infrastructure in place so that we can actually pilot the TRL4 into the next level of scaling in TRLs, and then move on, having the industry on board. So these stakeholders should be together. And we need to also change, that kind of a model in which we are funding the scientists or the institutions in a tranche manner of milestone linked ones. Can we have it as a single window? that is going to really help the scientists with that flexibility of handling the funds in a manner whichever comes prior as per the prioritization, they can seamlessly switch and then use the fund in a flexible manner. That helps them in reaching the goal better and faster. And the third thing where the AI ML digital twins integration helps the scientists reduce the timeline also to fast track their innovation into the translation by cutting down the timelines for piloting. And most importantly, if you have a commercialization arm, as we are trying to do at CSIR as part of the reforms that we are coming up very soon, is where we want to have the production partner also on board, the industry, so that we can form SPVs or JVs with ministries as well as the industries. The industry can come on board with a letter of intent prior, during the designing itself at TRL 1 to 3 with no monetary investment. So this de-risks their investment, and thereby at TRL 3 they can come in with their investment. And this way I think this is where DST has played a major role through ANRF funding for RDI funding to industries to boost this innovation, reach the market. That is going to help. And lastly, one point which is the most important is the cultural integration of the scientists, engineers to work with the industry engineers and seamlessly working with reduction in conflict of interest taboo on them, such that they can really make a difference to this particular movement of from the innovation in the lab to the market.
Thank you. Thank you very much, Sailji Garu. See, this brings one more question. Bala, I want to pose this to you. While she talks about this building, but there are people who talk of different languages. For example, if you talk to a person in an industry, he says, I want a technology yesterday, okay? Whereas you talk to a professor like Pradeep or B.S. Murthy, we talk of in terms of PhDs, okay? So that means a minimum of 5 years or something like that as for something to come out. And you now, I think thanks to our Honorable Prime Minister, has put up a strict guidelines that to say that by 2030 that your imports have to be brought down by 50% or something of that nature. So, and of course, DRDO must be working very hard and how to give technologies to services which will be able to implement it soon. So how do you think that this gap can be filled so that we fast track, as Madam is talking about? What is the impression from the DRDO side? You are leading a big lab in DRDO. How do we fast track it so that we get these technologies quicker?
Thank you. I think all of us will recognize and realize just from the proceedings of these 3 days that we are living in times of rapid change. And I think, and some of these, what I'm going to say may sound like cliches, but they have a lot of value and substance. And I think the most rapid change that needs to happen would be in our mindsets. So rather than, I think Professor Murthy, in laying out the question, talked about academicians and PhDs, research labs like ours which are caught in between industry wanting something yesterday and the user wanting it day before yesterday, right? So it's obviously we talk in different units, we talk in different things. And I would think that there is no single unified solution to this. It will be on the scale of a grand challenge almost. But perhaps a very good pathway to that would be to look at commonalities, to look at priorities. Professor Kulkarni talked a little bit about that, and he said in that vision document they're going to talk of prioritizing. So there is definitely, and this concurrent thing, I would also like to give another example from maybe from quantum physics, where you put periodic boundary conditions and you make it into a circle. So it is not just a linear development, and especially the ICME, AML kind of models, where every step from material design, discovery to deployment talk to each other, including the very important and very time-consuming steps of certification. I think that has to be handled, and then we will not have a single model. So it's very important for us to look at, there are three main things. One are people who bring experience and expertise. Others, of course, the time that it takes, and then the cost. And of course, we are now interested in doing, time is the main thing that we are looking at. So the whole idea is to how to get that down. And in fact, Pawan in his talk talked about additive manufacturing, revolutionizing things, making 100 parts to 1 part. And what used to take months and years can be done in a matter of a few days to a week. So that will be possible for certain products. Certain other products it will not be possible. So we'll have to look at it in terms of technology gaps, infrastructure gaps, and look at what are the products. So we'll have to work together like what Shailaja ma'am said, and then we'll have to take it from there. But I think, therefore, what was 15 plus years, today certainly the most complex, most critical materials, and for certain very critical systems, class 1 aero components, for example, we are trying to bring it down to 5 to 7 years with the aid of these advanced techniques. And there are some other things where it has been demonstrated that you can do it in the span of 9 months to a year. So I think, but it does need unified, collaborative, complementary effort from everybody.
Thank you very much, Bala. Now, we have heard from two different types of labs, one CSIR, one from DRDO. I want to ask Subodh, in this fast tracking, while our Honorable Prime Minister gave us 20 years time, 2047, at least in certain fields, if we want to do it quicker, what can industry do to ensure that certain TR levels that academics like us, 1, 2, 3 is what we usually work on. So from there to take it to 8 or 9, where is the role of industry like yours, and what can industry help in ensuring that we reach our targets much faster?
I don't have a clear answer, but I have reflected on this for some time, and I think the problem is more grassrooted, at a grassroots level. If I look at an industry perspective, we grew up as managers in the company, and we forget that we're engineers, or we are made to forget that we're engineers. And I actually reflect on recently my visit to MIT, where there's a huge startup ecosystem which is working. There are PhD students who take up the startups, do lab scale, go to TRL 5, 6, and are ready for commercialization by themselves, right? And I don't think we have built this ecosystem here in India. And at the ground level, till we promote innovation and recognize innovation in children and nurture them, I think it's going to be a challenge for all of us. And the second important thing I see personally, which I experience, is we don't have the socio-economic culture of accepting failures. And I'm not talking about process failures or complex failures which happen because of the environment or something outside your control, but intelligent failures, we don't celebrate that. And therefore, okay, let me reflect on a different point. So sometime 2002, 2004, the steel boom started in the world, and if you recall, China is now making millions and millions and billions almost of steel. And probably India was at the same stage at that point of time, right? Maybe not in terms of demand, but in terms of the ecosystem of steel, it was there, right? And suddenly, you had these companies now of Shagong, SISDs, and who are the design engineering companies, who are the capital equipment manufacturing companies whom you have never heard of in last 15, 20 years. 2002 onwards they came in. Even BYD, I mean, take any of the industries, whether it's automotive or whether it's steel or any manufacturing processes, they were not there. They just came in 10 years. And we had the HECs and the Mecons and there's nothing. We don't have a company who is able to help us give a capital equipment or design a capital equipment as per the industry needs, if at all we want to make something new. And I think this skill set is what needs to be nurtured in India, right? I see good examples of what MHI, Ministry of Heavy Industry, is doing with ISC on indigenization to start with, just indigenization. Do we have the skill set to indigenize components and or even SRTMI, which is the Steel Research Technology Mission of India, which is attempting to indigenize the capital spares that we import, right? Can we create an ecosystem of ancillaries which can just make components which build the skill set of scaling up things? Yes. Right? And I think that is the missing link which I'm not able to figure out in
Thank you. Thank you very much. In fact, he really brought out an important ecosystem that exists somewhere outside. For example, he mentioned about MIT having a lot of people working on innovative ideas. I think one way to reach our goal is to have a lot of industry on academic campuses, which does not happen. MIT is an example, Stanford is an example, so many industries on the campus. So if you want to really do that, one major hurdle that we always come across is IP problems. Okay? Do you have some thoughts, Mandar, on how do we bring out policies where when an industry wants to be on a campus of an IIT, let's say, or a TIFR, and how do we ensure that we have the right policies on the IP sharing? And do you have some thoughts on that?
Yeah, that's a very interesting question. I think we have we have to streamline and make it easy for this interaction to happen. So the ease of creating intellectual property and sharing with entrepreneurs who might be interested in it, or academics who want to become entrepreneurs, making that process easy is crucial, because every time there is an additional challenge in procedure that one creates, you lose some fraction of people who are excited about this. And so even for the case of collaborating with industry, this over-defensive approach of academia to say we have to be very protective about it, I think that slows down the process of sharing with industry. So I think there needs to be kind of a uniformity across institutions in India. What are the rules of engagement, so that unnecessary institution level procedures are reduced to enable more of this interaction with between industry and academia.
Thank you. Thank you very much. One last question I want to pose to Sailja Garu. See, one thing that we have observed in India is whenever we were denied a technology, we have excelled in this. 3 examples that come to my mind: ISRO, TEC, missile technologies, or atomic energy. 3 areas where I think we are no less than any so-called developed countries. But rest of the areas where we were able to import technologies, we found that we found it easier, and while as a result we did not move. In all the other 3 areas, there was a kind of a mission mode approach. Set a target that I want to achieve. For example, ISRO keeps on talking about what is the next mission. Okay, set a target and bring people together. Okay, I want to ask her to address this question of collaboration. I always believe that collaboration is key to growth. Okay, in this direction of Viksit Bharat, how do you think partnerships? Okay, I think CSIR has done bringing various labs together on some trust projects and things like that. Okay, so what do you think India should do in case of advanced materials and manufacturing? Should there be some kind of clear mission mode approach in this area so that we should be able to achieve where we want to achieve?
Thank you, Professor Murthy. Again, that's a very, very interesting question, and I always love this kind of a question because this is where we have to break barriers and not work in silos, but come together as a mission-oriented approach. We form a consortia of the academic institutions of excellence that are working in R&D and bring in the industry folks on board, and also the startup ecosystem. To build this ecosystem, when you do that and also have the production partnership with the right SPV formation I was telling you, this is possible. And if we can only do that, then there's no stoppage for us to build that pipeline from innovation to market or innovation to industry. So in order to do this seamlessly, it's these kind of partnerships help in a big manner. Right now I see the partners sitting on this podium itself. If we can come together, bring our expertise onto the table as stakeholders, involve the industry right from the beginning, formulate the projects with a very focused goal of mission orientation. We have done this during COVID time, Professor Murthy.
Definitely.
Under pressure, when there is a need and demand, we all function very well.
Exactly.
And that is reflected well during COVID time, where we came up with vaccines that was needed. And similar kind of an approach, if we have, by bringing all the stakeholders together, make a consortia and give them the responsibilities, and you have the industry also on board, I think it can happen, and this can very nicely formulate a structure to make it, to ensure that that Viksit Bharat dream can be achieved. Because already we spoke about the fast tracking, which normally takes 8 to 9 years time. We can reduce it to 3 to 4, 5 years time of advanced materials to be manufactured and come into the market. That can happen by formation of this consortia, I would say.
Thank you so much. Basically, we need to feel that urgency, that if you don't feel the urgency and that I need to achieve it in a mission mode together, I don't think we will be able to reach there. So it will only remain as another dream of us. And the dream, if it has to be realized, and people should feel the urgency, everybody sitting in this audience should feel that and come together from academia to R&D labs, like what we have from CSIR or DRDO to the industry that we have Subodh representing. I think that's something which is very important, without forgetting that technologies come through science. So the basic science, like people like Mandar do, are people like Pradeep started, and then he showed that that basic science can lead to technologies. I think that is something that we need to really take it as a possibly as a lesson or a kind of a small message from this particular panel and take it forward. So I think we have a small time. I kind of restrain my colleagues here not to speak a lot, so that we have some time for some kind of a questions from audience. If there are any questions, possibly there must be some mic passing on. I want my organizers to ensure that there is some mic provided to a few people. Maybe we will be able to take 2 or 3, but please direct your questions. I mean, this is not for you to give your opinions, but more on asking questions. You can possibly address any one of our colleagues. There is a lady waiting there. I think she raised her hand first. Introduce yourself in half a minute, maybe in 10 seconds, and then ask a question.
Hello, sir. I'm Payal Patel. I'm founder at Agropack Private Limited. And I'm an innovator in material, solving the problem of plastic packaging. The issue that we are facing, the biggest challenge, is finding the right certification, because it is a novel material and there is no standard which exists to solve this problem for something which doesn't have any plastic or plasticizer. It is not wood. We utilize coconut shells to make containers. How should we tackle this challenge as a startup?
Do you want to answer this, madam? Sailja Garu? Or I can ask Bala. Yeah, because they also deal with certification and much more stringent certifications in DRDO. So whoever wants to start, maybe Bala?
So this is one of the biggest pain points in the country in terms of materials development. As an entrepreneur, I'm sure you would have seen it, right? So the whole question is, when you develop a new material, how do you say that it is fit for purpose and it does go through so many things? And like you said about very stringent certifications, when you put something on an aircraft and a fighter aircraft or something like that, then you want to be absolutely sure nothing goes wrong, right? And especially when it's a manned system, it gets even worse, right? So unmanned maybe slightly less. And there is always a tug of war, a tussle between people who fire rockets and people who fly aircrafts. Okay. They say rocket is one time, but of course reusable launch vehicles will come, then again repeatability will come. Yes. So material property wise, for example, metallic alloys, creep, fatigue, then the interaction, all that matters. But if long duration, certain aspects, the long duration is 1200 seconds. Today their target is 150 seconds. Whereas for an aircraft engine component, it is 2000 hours of flying, right? So when you put a plastic kind of a component, then you have, the word plastic will trigger toxicology, environment, biodegradable. But the generic approach, therefore, what people can take, and this has to happen, unfortunately in the country today it is very scattered, is to look for, first of all, what is the requirement from the product side, and then from the manufacturing side and toxicology and environmental friendliness. And I think we need to perhaps, as a country, have some bodies which look at this. In the defense side, it is clear in terms of criticality, but even there, just to get into a bit of detail, The Aero certification is quite advanced. It has existed for several decades.
Yes.
But similar thing for example, for land and sea-based systems does not exist as a single entity. That has to come. And I think BIS is doing something for example, when it comes to food, when it comes to, common products and so on. But this steel, again, there's a lot of things that happens. But when it comes to consumer goods which are in the public general domain, packaging is one example.
Yes.
So cartons, cardboard boxes, who certifies? I don't think we have agencies. I think it's time the country does look at it. So I don't have a direct answer for you, but I do acknowledge that it's a main problem, and I think something, perhaps a forum as big as this, it can be put as something within the policy to look at and to develop such agencies.
At the same time, developing techniques by which you can, do this testing very quickly. Okay, so some kind of a fast track techniques which will still be able to give a result which can predict the life of the whole component. So definitely there is a lot to be done on that direction.
It definitely will have to be in an engagement mode, because if you know you're replacing something that is there, just look at what happens to that and how that is certified. Sure. And versus that would take care of the fitness for purpose, and of course the certification and testing is an integral part of it.
Thank you very much. Someone here, I thought, raised a, yeah. Yes, please go ahead.
Hello, I am Shashank Kumar. I am the co-founder of a company called Multi Nanosense. We make gas sensors. So my question is to you, Professor Murthy.
Oh.
So we've been engaging with academia for a very, very long time. We've had sponsored projects, stuff, all of that. But what we find is professors are more than 50% times engaged in administrative activities. So can this forum come up with an AI or something XYZ to like free up 95% of the times to real productive stuff, and maybe 5% gets done through just approvals?
Yeah, I mean, true, every professor wants to do everything by himself. But at the same time, I can tell you, at least my experience at IIT Hyderabad, there are quite a number of professors who have their own companies. Okay, we have been encouraging a lot. For example, we have gone to a level that an undergraduate student, for example, at the end of second year BTech, if they have an innovative idea, we say take a break now. We give you a diploma. And we give you 5 years time to come back and complete the third and fourth year. Ideally speaking, I don't want anybody to come back. After 3 years or 4 years, somebody should come back to me and say, sir, I don't need your degree anymore. So can we create such people? And there are quite a number of faculty who are helping in that, all that. So, kind of a mentorship roles they are playing. So, I mean, if you are interested, you can just come. For example, at IIT Hyderabad, we have 1.5 lakh square foot area building, just for innovation. Okay? So there are institutions, IIT Madras also has something of that nature. So there are things changing, quite a number of, for example, I just now have come from another session where one of our colleagues has 250 patents in 5G and 6G. Okay? He keeps on churning out patents, okay, on standards, particularly 5G standards and things like that. So there are faculty who more work on a fundamental aspects, do think of long-term science aspects, and there are people who trying to see how I can bring out quickly technologies and things like that. And there are ways of finding out how to overcome these administrative problems. I mean, being a director, I try to look at that aspect. When somebody needs to really focus on something, we say, okay, you don't need to be an administrator for some time. So we avoid giving them any administrative roles for certain period of time so that they focus on what they want to focus on. So that kind of a flexibility has to be created, and we are able to do that. Anybody else? Maybe she raised hand. So we'll come to her and then come to you, sir. And with that, we'll close.
Okay. Thank you. I'm Gayatri. We have a startup. Some of our nanotechnology products.
Happy to see that most of the questions are coming from startups.
We really have some practical problems
you.
that need your solutions. So we have few nanomaterial-based products in the TRL 4 to 7 range. So my question is both to Dr. Shailaja and Dr. Subodh. So now we have a particular product both in composites or, just material production, for example. What should be my set of activities, immediate activities, to be able to get into the actual market? Whom should I approach? We have talked to Tata Steel in a closed door in a conference. We have talked to CSIR Institute separately in a conference. But nothing, actionable plan comes out when we talk to everyone individually. So what should be my set of activities? We have the license. We would like to take it to market. What should we do? We also need some business plan, somebody to say, we carry some business plan, but that doesn't, see the light of the day. What is the right approach so that these products see the market? Thank you.
Sorry, what is the product you said?
We have,
Composites, you said?
yes, we have a technology for high yield production of graphene. We have some polymer-based composites, both on epoxies as well as, something like Dr. Pawan was talking about, composites based on various kinds of fibers. And also we have some coatings which can go on various products. Yes.
Should I?
I don't know the full thing, but the challenge which you're describing is probably the biggest challenge in India for the startups to go up to that level, right? As an industry, we work very closely with startups. Now, there's a core area for Tata Steel, and there is something that we're trying to build as part of new material business, which includes composites and graphene. So I don't know the details of what you're talking about. But there are challenges in both, right? Because an innovation needs a market commercialization, right? And it's not easy for a product which is not understood by and it's whose strengths are not known, whose benefits are not known, and value demonstration is difficult to the end consumer, right? Plus the angle which we just discussed about, there are no standards, right? So if graphene is really creating a value in HDP pipe, and therefore I can reduce the thickness of the HDP, but the BS standard won't allow me.
So just to add, we did talk to an automotive industry. So they, even to check, they wanted our composite in certain dimension and certain design that is useful to their company so that they could test. So where do I get that done? It is like, 2-3 meters long, in a very different shape that a lab cannot handle. So where should I go? Maybe a particular CSIR institute, for example, or that is where we are stuck.
Can I?
Yes, madam.
Yeah. See, once you find out the differentiator of your product, and with respect to the application, and somebody has given you a direction also. So once you have a clarity on that differentiator and the competitive advantage that your product has, accordingly, CSIR lab, which has that skill set and expertise, can help you, give you kind of a mentorship. If we have an incubation center there, then you could be helped with the acceleration of your technology, which will be product market fit based on the automotive industry or whichever the industry where the nanomaterial developed by you can be applied. So this way, you can always reach out to CSIR labs. You can actually reach out to me. I could connect you to the right lab, because we are a multidisciplinary organization with several laboratories of at least 37 numbers and different disciplines, 5 different disciplines, and it would be difficult for you to choose. So I can help you out, and then it becomes for you to escalate the scale at which you're doing and the level at which you have the product for arriving at that finesse and utility.
Thank you. Thank you very much. I think we need to close, but on a very important note that she has raised, saying that how do we, kind of handhold the startups like her to ensure that the light at the end of the day can be seen. At least not only in CSIR labs, even in academic institutions like IIT Hyderabad. For example, we have a Dean of Innovation, Translation and Startups. Okay? There is an Office of Innovation whose job is to find out faculty and students who are interested in innovative ideas. For example, in the last 5 years, we have 600 patents, filed by IIT Hyderabad alone. In the last 1 year alone, it is 220. This year, we set a target, Mission 365. So while we do that, the next office looks at how do I take this and which kind of industries I should connect to. okay, and there is a lot of effort happening. And even for outsiders also, we welcome them. If you are interested, you can write to me. I can possibly find out from our technology transfer office, is there any industry in that specific area who may be interested. And then finally, and ensure that we have the right kind of ecosystem for the startups to finally see their products the light at the end of the day. I think that is very essential. Bala, you want to
Yeah, very
add
quickly,
something?
I know we are running out of time, but
I don't think we have time, sir.
So
1 o'clock is the hard stop, I was told, and I have 2 minutes for 1 o'clock.
So just
Please.
to close this, the important point is I think it is again a very common problem, right? I mean, even if you've been attending all 3 days, even big companies face this, there's the so-called value of death of the most promising result. I mean, hardly 2 to 3% eventually make it to a final product that is used consistently, right? So one of the things is you look at possibly potential applications, right? Because the moment there is a user pull for something, it is much better than pushing it from the developer side. That said, it's not that you should stop this, but you should also look, in fact, that is where network and other thing really helps, is to look at potential applications, because something may need from, say, you are very small in a bottle, milligrams or whatever, then going to a meter long may take a lot of effort, a lot of resources and time. But if you can say use as dispersoids in something else, that application could move much faster. So I think taking the help of what Shailaja ma'am said and others in different organizations, the startup incubation that IIT Hyderabad offers, use these avenues to find potential applications and see where it can replace current products or even unmet demands. I think that's the way to go. Thank you.
Thank you. Thank you very much. I would like to thank all the panelists and also active participation from the participants. Definitely, there is a clear indication that comes out that we need to focus on the science and push the boundaries to ensure that we reach our target of Viksit Bharat as quickly as possible. At the same time, address the kind of problems that our friends in startups are echoing, and to see how do we strengthen the startup ecosystem to ensure that we reach our targets as quickly as possible. Thank you. Thank you very much to the organizers for this opportunity.
I convey my thanks. I convey my thanks to all the panelists and the moderator for this enriching dialogue. So we now request the session chair to felicitate the panelist and the panel moderator. Yeah. Firstly, session chair is requested to felicitate Dr. Ramalingam. We request the session chair to felicitate Mr. Subodh Pandey. Professor Mandar Madhukar Deshmukh. Dr. D. Shailaja. Finally, I request DGCSIR to felicitate Professor B.S. Murthy. Sir, we sincerely thank you for ably leading the panel discussion. Can we have a group photo, please, with the panelist and the moderator? So kindly just be on the stage, sir. I would like to invite our 4 speakers for the day and all the thematic committee members for the photo, please. A group photograph. I request all 4 speakers for the day and all thematic committee members. Conveners may also please join. Thank you so much. I would request Dr. G. Mahesh to kindly give vote of thanks. Yeah?
Use this podium. It's my privilege to propose this vote of thanks. So at the outset, I would like to thank the chair of the session, DGCSAR, Dr. N. Kaliselvi, for her esteemed presence here with us and also for her inspiring opening remarks this morning. I would also like to thank the keynote speaker, Professor Kulkarni, the invited speakers, panel discussions, and as well as the chair. I also wish to thank the expert committee members under the chairmanship of Professor G.U. Kulkarni for putting together this wonderful program. Particularly, I would like to thank from the DST side, Dr. Shama, from the ARCI team, Dr. Anandan, and the team coordinators for their many help. So thank you all very much.
Concluding the event, we convey our thanks to all the dignitaries, speakers, panelists, and delegates for their participation in this stimulating session. Wishing you all a wonderful day ahead at the Emerging Science, Technology, and Innovation Conclave. Thank you.